Now, if u1 up to up is a collection of non-zero vectors, and y is in part of the n with y equals c1 u1 plus dot 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 plus cp up. We already know what all those are going to equal. Let me give myself some more space. The c1 is y dot u1 over u1 dot u1 plus y dot u2 over u2 dot u2 times u2 plus dot 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 plus y dot up all over up dot up times up. And we just did all this. If you think about this, we would have this portion right here is the projection of y onto u1. This guy right here is the projection onto u2 of y, and so on. This last thing out here is the projection onto up of y. As usual, the inspiration that we need for visuals comes from R2. So in R2, we'll have something like this. Y will equal y dot u1 over u1 dot u1 u1 plus y dot u2 over u2 dot u2 u2. So both of these are projections of y onto those respective vectors. So we'll have something like this. I don't know if I need to draw axes or anything like this, but what I'll have then is, let's call this u1. We'll call this u2. Remember, the vectors u1 and u2 are perpendicular to each other. And out from the middle of them somewhere is our y. Now, if I project my y onto u1, it may or may not be long enough. I may have to scale that u1 a little bit in order for the y to project onto it. And the same thing over here, it'll project onto this one. So this piece right there, this vector that only goes that far, that's this guy right here. Let me see if I can draw. That's precisely that vector right there. And this vector, it looks like u1 was long enough, or maybe I need a little bit shorter of a vector for u1, but this guy right here is that vector. So you can see that y is able to project onto u1, and it's able to project onto u2. So it's able to project onto two vectors at once, and by this, if you have an orthogonal basis, you're able to project onto all of the basis vectors. And obviously, after we get to, obviously when the size is bigger than 3, we cannot visualize what's going on. Another definition: an orthonormal set an orthonormal set is an orthogonal set. Oops, I made a mistake there. An orthogonal set such that when I take the norm of any of these vectors, like ui, take the norm of ui, that equals 1 for every I so the norm of each vector is 1. Basically, it's an orthogonal set of unit vectors. Any non-zero vector can be normalized. So, as an example of that, we'll let u equal simply 1, 2, 3. And then the norm of u will equal the square root of 1 squared plus 2 squared plus 3 squared, which equals the square root of 14. Now then, 1 over the norm of u times u will equal 1 over the square root of 14 times 1, 2, 3. Now let's compute the norm of that thing. And I'll write it in one more step just to make it clear. 1 divided by the square root of 14, 2 divided by the square root of 14, 3 divided by the square root of 14. So there's my normalized u. In fact, let me give it a name. Let's call it n for normal. All right, now let's take a look at the norm of n. This equals the square root of 1 divided by the square root of 14 squared plus 2 divided by the square root of 14 squared plus 3 divided by the square root of 14 squared. That equals, I better make my square root bigger, 1 over 14 plus 4 over 14 plus 9 over 14. I think you're going to see that all those over 14s add up to be 14 over 14, or this is equal to 1. So you can take any non-zero vector and normalize it simply by dividing by its norm. So if u is not the zero vector, then 1 over u times u has length 1. It's been normalized, or it's a unit vector, whatever you want to call it, a direction vector even if you'd like. Theorem. If u dot v equals 0, make my v more v-like, then u dot alpha v equals 0 for any real number alpha. And that's all because when you do u dot alpha v, you're allowed to pull the alpha to the front, and you'll end up with u dot v, which equals alpha times 0, which is 0. So there's really not much to do there. Very simple little theorem. Now, one thing you want to note, if we normalize a non-zero vector u, so I'll get this thing, this new vector is a multiple or parallel of u. Theorem. Let u be an m by n matrix. Then we have U as orthonormal columns if and only if the transpose of U times itself is equal to the identity matrix. I'll put an I sub n because U transpose will be an n by m matrix. So you'll have an n by m times an m by n. That'll be an n by n. So if you want to maybe put times n, I don't really care what you put for that. Let's do the proof. Write U equals U1 UN. Those are my columns for the matrix U. Now, what I want to do is, while I'm here, is I want us to make sure that we know the sizes we're dealing with. Obviously, this has n columns. Each vector is size 1 by m. So that's an m by n matrix there. Now look at U transpose. We'll have U1 transpose all the way up to UN transpose. Now these are row vectors, and this is an m by m matrix. So when you multiply the two, as I said, you'll get n by n. Let's go ahead and do U transpose times U. So U transpose times U. I think this is a good exercise in seeing how matrix multiplication is done on a vector-to-vector basis. So we'll go ahead and put these things in. I have U1 transpose all the way down to UN transpose times U1 all the way up to UN. And now when we do this multiplication out, remember I said we're going to have an n by n matrix. We have U1 transpose dotted with U1. If you remember how this works, you take the first row and dot it with that column, and that will give you the first entry in the matrix. And then what we do is we take this row and do it to the next column. So we'll have U1 transpose. So we'll take that and dot it with U2. And you'll continue in this fashion to get UN transpose dotted with UN. Oops, I made a mistake. U1, sorry. The next row will do the same thing. Pretty much I'll have this time U2 transpose dotted with U. What we do with U1. And then we have U2 transpose dotted with U2 all the way until we get to U2 transpose dotted with UN. And you keep going until we get to the very end. Here I'm going to have UN transpose dotted with U1, UN transpose dotted with U2, all till we get to UN transpose dotted with UN. Now this is equal to the following matrix: 1, 1, 1, dot, 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 1. Maybe I should have made my matrix bigger. I'll make this side a little bit bigger. With zeros everywhere else. This is true if and only if ui dot ui equals 1 and ui dot uj equals 0 for all I not equal to j. So what does that mean then? This is the same as u1 up to un being orthonormal. Another theorem, once again, let U be an m by n matrix. Let U have orthonormal columns. Right? If x and y are vectors in R to the n, then A, the norm of ux is the same as the norm of x. So basically, when you multiply x to u, it preserves the length of the vector. For B, we have ux dot uy equals x dot y. So it's as if u did nothing in that particular instance. And for C, ux dot uy, I think I should probably put parentheses around these things. That equals 0 if and only if x dot y equals 0. And you can see that C is going to follow once B is true. C is obviously going to be true. So proving this, just proving A and B should be enough to finish off the whole thing. So let's do it this way. For A, let's do ux, and I'm going to square it. So remember, that's ux transpose times ux. Well, you may not remember this, or you may, I don't know. But when you take the transpose of a product, you can get the product of the transposes, but it's in reverse order. So I'm going to get x to the t, u to the t, for that part, times ux. I can use associativity in this matrix multiplication to get x transpose u transpose u times x, and that's x t, and we just saw that u transpose u is equal to I, and so that equals x transpose x, which is equal to x dot x, and that equals the norm of x squared. So we have ux squared equals the norm of x squared. When we take the square root, we have a positive and negative possible solution, but obviously we throw away the negative solution when we take the square root to get this, because we will not have a negative length. So part A is easy enough. For part B, we have ux dot uy, that equals ux transpose times uy, and same deal as before, we're going to get x transpose u transpose u times y. The u transpose u will be I, so that'll be x transpose y, which, as we know, that is x dot y. Part C, I'll use a word that is famous among mathematicians, and that's trivial. As an example, let me create a matrix and then orthonormalize it. So I'll show you how this works. M is going to be the following matrix. It's going to be 3 by 2. 1, 2, 3, then negative 3, 3, and negative 1. So I'm going to call the first column C1 and the second column C2. First thing I want you to note is that C1 dotted with C2 is equal to 0. Next, if I take the norm of C1, I'll get the square root of 1 squared plus 2 squared plus 3 squared, which equals the square root of 14. The norm of C2 will equal negative 3 squared plus 3 squared plus negative 1 squared. And that there will be the square root of 19. So to make a matrix like the theorem, we are going to normalize the rows, well actually the columns. We're going to normalize each of these columns. The first column I'm going to divide by the norm of C1. And I'll do the same thing for the second column. And notice that what we have here is a 3 by 2. Let me then do U transpose times U. So U transpose then will be a 2 by 3, and the first row will be 1 divided by the square root of 14, 2 divided by the square root of 14, 3 divided by the square root of 14. The second row will be negative 3 divided by the square root of 19, 3 divided by the square root of 19, negative 1 divided by the square root of 19. And I'm going to multiply it by U itself. Let me put its columns back. And the other column. And let me go ahead and multiply it all out. So I'm going to have, what am I going to have here? I've got a 2 by 3 times a 3 by 2, so I'll end up with a 2 by 2. But something tells me I'm going to need some space here because I got a lot of stuff going on. So while it's a 2 by 2, I'm going to use extra space. All right, well, let's see what we have now. We take this row times this column here. So I'm going to have 1 over radical 14 times 1 over radical 14, which should be 1 over 14. And then I'm going to have 2 over radical 14 times 2 over radical 14. That'll be 4 over 14. And then plus 3 over radical 14 times 3 over radical 14 is 9 over 14. All right, let me go ahead and do this part, this row, now times this column. So I'll get 1 over radical 14 times negative 3 over radical 19. That will be negative 3 over radical 19 times 14. I'm not going to bother multiplying it out because I anticipate these things will end up coming to a 0 anyways. Now I'm going, let's see, what's next then? I have 2 over radical 14 times 3 over radical 19, so I'll get plus 6 over radical 19 times radical 14, plus, and then finally I'll have 3 over radical 14 times negative 1 over radical 19, so I'll get negative 3 over radical 19 times 14. Then I'll move on to the second row here. The over 19s times the over 14s, so the second row times the first column. I'll get negative 3 over the square root of 19 times 14. And then I'll get 3 over radical 19 times 2 over radical 14. So I'll get 6 divided by the square root of 19 times 14. And then finally, negative 1 over radical 19 times 3 over radical 14 will be negative 3 over the square root of 19 times 14. And then finally, I move on the second row times the second column. Notice they're all over radical. They're all over radical 19. So I'm going to have negative 3 over radical 19 times itself. I'll get a 9 over 19. Then I'll get 3 over radical 19 times itself again, so I'll get another 9 over 19. And then negative 1 over radical 19 times negative 1 over radical 19 will be positive 1 over 19. Let's see where we end up at. For the first one, 1 plus 4 plus 9 is 14. So 14 over 14 gives me the one that I want. Here they all have the same denominator. Negative 3 plus 6 is 3. Minus 3 is 0. Then I have negative 3 plus 6 minus 3 is 0 again. Then 9 plus 9 plus 1 is 19 over 19 is 1. So all I need to do then is fix that particular side, and this demonstrates the theorem. If U is a square matrix with orthonormal columns, then U is invertible. So we can see that U transpose times U equals the identity matrix. That implies that U transpose is actually equal to U inverse. Definition. Suppose U is a square matrix. U is called an orthogonal matrix if U is invertible and U transpose U equals the identity matrix. And once again, let me just remind you that that is the identity n by n matrix. If U is an orthogonal n by n matrix, then the columns of U span Rn. And we know that if it's an invertible matrix, then the columns are linearly independent. And since they're linearly independent, then you have n linearly independent vectors in Rn. Well, I pretty much have said it. So since U is invertible, its columns are linearly independent. So that gives n linearly independent vectors in Rn. Thus, the columns span Rn and the columns form a basis for Rn. If U is an orthogonal n by n matrix, then the rows of U form a basis for Rn. The proof is really simple. U transpose times U equals the identity implies that U transpose is invertible. So that means that the columns of U span Rn. Sorry, columns of U transpose span R to the n, which implies that the rows of U span let U and V be orthogonal n by n matrices. Then, if I look at UV transpose times UV, this is similar to, we know it would be the identity if it were just U and V, but check this out. Because the way the transpose works, we have V transpose U transpose times UV, and we can associate V transpose U transpose U times V. We know that that's VT I V, is VT V, which equals the identity matrix once again. So this implies that UV is invertible. And UV inverse equals UV transpose. And you can adjust that for any product of matrices that you want. You can do U1, matrices U1 up to UN, and work something like this. Suppose U is an n by n orthogonal matrix. Then its columns form a basis, well, orthonormal. Let's see it. Then its columns form an orthonormal basis for R to the n. So the proof of this, well, we would know that U transpose U equals I. We already know that that is exactly the same as the columns of U being orthonormal. So we've got that going for us. And the fact that we have, since there are n columns in U, the collection, well, I should say the columns, I like that better. Columns span R to the n. So, or whatever else we want to look at. The dimension of them is n. There's about 100 ways you can possibly say this, but it's pretty evident. The mapping x into the projection of x onto a line is a linear transformation. And remember, the L, of course, is the span of some vector u. But just remember how this worked. The projection onto L of x was equal to x dot u all over u dot u times u. And of course, u can't be the zero vector for this to work. So now let's take a look at the projection onto L of cx plus dy. Put those into the spot where you see an x above, so we have cx plus dy dot u all over u dot u times u. That equals, let me break up the numerator of this, so I have cx dot u plus cy dot u all over u dot u times u. Let me break that fraction up. So I get cx dot u all over u dot u times u plus cy, that x has an arrow above it, dot u all over u dot u times u. That was a d. And boy, I make mistakes left and right here. Put that d in there. I can factor the constant out. So I've got the constant times x dot u all over u dot u times u plus d y dot u all over u dot u times u. And of course, this is the projection onto L of x plus the projection onto L of y. And I'm not quite sure I said it, though. I should say that L equals the span of u, since the projection onto L is really the projection onto u, but the L is there so that no matter what, you can project onto something. If I say a u and the u happens to be too small, then you don't have enough to project on. You have to lengthen the vector in that case. Sometimes you need to be shorter. But if you have a line that goes from negative infinity to infinity, you're definitely going to have enough space to draw a projection. Let me move on. I should put this in here. So that way, I'll put a dot after them too. That way you can see that that is a linear transformation. Is our inspiration. I want to start with a vector that's not equal to the zero vector, and I want to let L equal the span of that vector. So let's say L is there. And then we'll say U is maybe just up to there. And then let's have Y. And then it's going to project onto L like so. Now, what if I continued the projection through and did the same amount of length on the other side and got a reflected version of Y on the other side? We'll call it REFL onto L of y. Okay, so notice that if this vector were to go all the way to here, this vector that starts here, I'll put a big dot, and ends here. So let me map it out here. Starts here and ends here. We call that one the PROJ onto L of y. Now, if you do your normal stuff to geometric stuff like the following, I'm drawing dotted lines here, so that you can see that this diagonal is equal to the sum of the vectors y plus reflected y. So I have y plus reflected y is equal to the length of this diagonal, which is twice the projection. So 2 PROJ LY. And what that does is that leads me to a definition. So the inspiration is in R2, but the definitions are for Rn. So I'm going to define REFL onto L of y to be equal to 2 projection Ly minus y. And then what we get here is that x into REFL onto L of x is a linear transformation. So what do we have? Let's take Cx plus dy goes into REFL onto L Cx plus dy. And of course, according to the definition that I just had, that is 2 projection onto L of Cx plus dy minus Cx plus dy. But we just showed that the projection thing was a linear transformation, so that I know that that is C times 2 projection L of x plus D times 2 projection L of y. Technically, you can factor out the 2 after one more step. I just decided to do it all in one step. And then if I carry the subtraction through, it goes like this. And then what I can do is bring a C and have 2 projection Lx minus x plus D times 2 projection L of y minus y, and that equals C times REFL onto L of x plus D REFL onto L of y. And that's what we needed to show.